Okay guys, so today I'd like to give you a tutorial on how to compute price of call option using evaluation of partial differential equation in Mathematica. Okay, so firstly I need to set up the partial differential equation, and afterwards we are going to tackle the partial differential equation in Mathematica software. So let me firstly begin with a definition of the partial differential equation, so that everything is perfectly clear. I'm not going to go to the derivation. You can Google it out. It's pretty simple. The core point here is to focus on the implementation. Okay, so let's say that I denote V, the option value. Okay, and more precisely, V is subject to two variables as of t, which is the spot price, and t, which is time. Okay, so to make it complete, this is the spot price of the underlying, usually share, t, sorry, t is time. It's quite obvious. It's the usual notation. And then we have sigma, which is the volatility of the underlying, and then we have K, which stands for strike price. That's the price that determines whether you exercise the option or not. Okay, and the option can be call or put. Okay, I hope you know all the stuff I've written here. I know I'm missing one more thing. Yeah, there is free rate. R risk free rate. Okay, so now it's complete. So we'll basically use all these variables. I don't know why it's stuck. To set up a partial differential equation. Okay. The partial differential equation of Black-Scholes formula for Black-Scholes is partial of, is it doing something or not? Doesn't seem to be working. Okay, so let me just load it one more instance. Yeah, hopefully it works now. I don't know why it is frozen. So it doesn't work either. Where is it? I hate when it freezes. What's it called? Map type. Okay, so let's kill this. One more try. Okay, so let's assume that we are using the previous variables, and now I'm going to set up the partial differential equation. Okay, yeah, now it seems to be working. So we have partial of v with respect to time plus s of t times partial of v with respect to s sub t plus 1/2 of sigma squared s of t squared times partial derivative of the second grade. Oh, sorry. Just like that, minus risk-free rate times v equals 0. Okay, so I don't know why it freezes all the time. God damn it. Cancel. I'm suspecting the 64-bit system because this application probably is not for 64-bit Windows. Well, what I'm trying to tell you is that we have this partial differential equation which somehow puts the value of the option and its variables into unique relation, okay, into unique relation. And you can also see that nowhere, for instance, the variable k appears, the strike price. Well, that's because this is just a part of the partial differential equation, because for partial differential equation you also need the boundary conditions, okay, and there are 3 boundary conditions in the case of Black-Scholes. So we know that for sure if it is call option, okay, basically the boundary conditions determine whether it is call option or put option. I will assume this is a call option, so I'll say that v as of t at the maturity of the option equals max from as of t minus k and 0. Okay, this is the payoff of the call option. And there are 2 more boundary conditions. We know that when the spot price of the underlying goes to infinity, and there is at whatever time the option of the option value will also go to infinity. Okay, I cannot use the panel over here because it has frozen. Okay, so I hope you understand this this notation. Okay, when the spot price goes to infinity, the value of the call option also goes to infinity at any time. Okay, and the last equation is when the spot price is 0 at any time, the value of the call option also is 0. Okay, so we are using all the variables. We have defined ST to be spot price. This sigma means volatility. R is risk-free rate. K is strike price, and big T is maturity. Okay. Okay, so this is basically Black-Scholes partial differential equation, and it is specialized for the call option. The call option is defined basically by the boundary conditions over here. Okay, I'm sure that after this this tutorial you'll be able to set up partial differential equation with its boundary conditions for put option. You would keep this this equation the same, and you would just change the boundary conditions. Okay. Okay. So, well, having defined the partial differential equation, it remains to tell the software to solve it. Okay, we will have some parameters. We will just arbitrarily choose sigma, risk-free rate, time to maturity, and the spot price at time of 0. And we would like to give this. We would like to be given, based on this set of equations, some result. Okay. Okay. So here I am in Mathematica. I'll make this so that you can see it completely. So, well, let's look at this equation once again. This equation is very difficult to solve algebraically. So Mathematica won't do that. Actually, the thing you have to do is to use numerical implementation, which means that Mathematica actually computes the value of the call option at some kind of grid that it creates, and then it can determine the value of the call option at every point. Okay. So then you can choose any point on the grid, and it'll give you the solution. Okay. So let me just begin with the parameters. Let's say S0 is $10. This is the price of the underlying at time of 0. Then we have big T to be equal 1, which means that the time to maturity is 1 year. Then let's say sigma is 0.3, which means the volatility is 30%. Okay, risk-free rate R is gonna be 0.05, which means 5% is the risk-free rate. And let's say K is also $10. So you will exercise the option if the spot price of the underlying is above 0 at the maturity. Okay, so those are the parameters. I hope I'm not missing one. Okay, yeah, this should be complete. Fine. So I have the parameters, and now I need to set up the partial differential equation as written here. So like I said before, we are going to tackle the equation numerically, okay? Otherwise we are not able to compute it. So we define a solution variable called sol, which will hold the result of the following. We call function called ndsolve, ndsolve. Be careful about capital letters. And so this is a numerical solution to differential equation. Okay, dsolve means it involves some differential equation, and n means numerical approach. Okay, and now I'm going to type this partial differential equation. So I'll write d of v as t well, what this basically means is that this is the partial of v with respect to t. Okay, d means like differentiate, and differentiate v with respect to t. Okay, so I have written basically the first term, this one. Okay, maybe I'll do it like that, so that you can see it. Okay, now I'm going to write the second term, plus s times, now comes again d, and the arguments are gonna be v as of t and t with respect to s. I think I've made a mistake over here. I'm not sure whether here should have been r or not. Let me just look at over here. Yeah, I'm missing this r over there, so let me just fix this issue like this. Now it's fine. So here shall be r times s times derivative partial of v with respect to s, okay, plus 0.5 times sigma times s times s. Okay, I could write it like squared, but I don't care. Times d of v of s and t. But now how to tell Mathematica that it's gonna be second partial differential equation with respect to s. Well, you have to do this. You have to say s and 2. It basically tells Mathematica to perform second order differentiation with respect to s. Okay? And minus r times v, and that all is all equal to 0. Don't forget that this is double equal sign. Okay, and just behind that you put the boundary conditions. Okay, so we are going to put here the boundary conditions we have specified here. So we say that the payoff will be v s, and the terminal time is t equals max s minus k 0. Okay, so that's the first boundary condition stated over here. Secondly, we say that we cannot put infinity here. Okay, that would confuse Mathematica. So we choose some arbitrarily large number that the underlying will probably never attain during this 1 year period. So we say, for instance, 100. T will basically, it will get very close to 100. So we say it's gonna be 100. You could put 1000 here, I don't really care. So this is not exact. Okay, this is not exact. It just substitutes this information that it goes to infinity if the spot price is infinity. So this is just the approximation of this boundary condition. And yeah, as well, double equal sign. And the last boundary condition says that if the spot price of the underlying is 0 at any time, the value of the call option also equals 0. Okay, and just afterwards, so this is one piece of code. This is just one block of the ndsolve function. Then you have to add, well, that you are solving for v, and you are going to evaluate it numerically for s between, say, 0.1 up to the boundary condition, which is 1000, and for t between 0 and 1 for t. Okay, so this should be basically it. We have specified the problem, and now we are going to let Mathematica solve it. So once again, this is the fundamental PDE. Those are the 3 boundary conditions and here are some Mathematica parameters which tells Mathematica solve for v and numerically evaluate for s between 0.1 and 1000 and t between 0 and the maturity, which is 1. Okay, so notice that, well, the 1000 here must correspond to the 1000 here. Okay, there is somewhere there is a mistake. I'm really confused. The function appears with no arguments, so let's see where it is. Where is the problem? Here we have the arguments. Here we also have the arguments as well. I get it. Over here is missing. S T. Okay. So one another try. Boundary and the initial conditions are inconsistent. Oh, I don't care. Let's see what it has returned. So this is basically some kind of solution. It doesn't tell you explicitly anything about the grid, but we are able to obtain solution from this output. Okay, so we say v as of t. Take v as of t and put in the solution. And let's say we want to check what's the price of the option when the current price as 0 is 10. So I put a 0 and we want to evaluate it at times 0. And here we get the output. Okay, so this is the evaluation of the call option. This is the price, the option premium. I'm just wondering why it has written this, because this is normal. Maybe it's because we should have here 1000 minus k. Yeah, that's probably it. Yeah, it hasn't changed anyways, because this is just a technical issue. It approximates this kind of boundary condition. Okay, so this is the price of the call option. I'm going to check that solution in Excel. Forget this thing. Okay, so this is a 0. The result, the exact result is 1.43, and nearly the same I got in Mathematica. Okay, but anyways, we can obtain some more information from Mathematica, because the solution is basically a grid. It's a grid, and we are going to plot the grid. Okay, to see this, let's see what I'm typing here. I'll want Mathematica to perform plot 3D of this thing for s between 0.1 and say 25, and for t between 0 and 1, and this is so-called pricing surface. It shows combinations of the spot price, which is on this axis, and time variable, which is on this axis, and its value, which is plotted in the vertical axis over here. Okay, so that you can verify that somehow when you take our values like 10 and 1, 10 and 0, so 10 would be somewhere over here and 0 is over here, so here it should correspond to 1.4226. Let's see if it is possible. It's not yeah, it might be that. It should be that. You can see that 1 is somewhere over here, and if you take the value from here, you really have something from 10 at time 0. Okay, so at this point, basically this point on the pricing surface is our solution. Okay, however, if we choose a different point, let's say the initial price want to be 10 but will be 8, this number will grow and we will be moving this this direction. Oh, sorry, this number will get smaller and we will be moving that direction on the pricing surface. Okay, see this. So the number has substantially decreased because we have moved to the left. We are somewhere over here. Okay, and now if we move to maturity, that means we are moving at this axis, like at this axis, we'll get a number on this border. So if I say we are at maturity, so we are at this border, we will get the price to be 0 because 8 is over here. Okay, and if we choose the price to be, well, 20, we get this point, which is supposed to be something like 10. Yeah, it must be 10, of course, because of the boundary condition. So if we choose 20, we get 10. Okay, so basically this pricing surface tells us all the information about the possible combinations of time and the price of the underlying. Okay, so I think and hope it helped you a little bit to develop your skills in mathematical finance with Mathematica, and feel free to visit my channel again.